Hello everybody and welcome to Handmade Hero Show. We code a complete game live on stream. Before we get started today, I want to just make everyone aware, as I will for the next few streams, we do have a Discord now. It is very active. I think we've got over 600 people on there already, even though it's been up for only a couple days. We are trying this out because so far, I wasn't thrilled with Twitch chat. It's kind of cumbersome. It's less permanent. It's just not that useful. I don't like Twitter. It's a trash fire. And so I just wanted some place that we could manage, and that made it easier for me to basically like moderate, right? So we have a Discord now. If you want to join it, we'll be putting links up to it soon as well. But if you just go to discord.gg/mollyrocket, that'll take you right to the invite. You can join up. We're close to 700 members now. Never mind. And I would highly encourage people to check it out. It's been good. People have been very civil on there, and I am kind of popping in from time to time to enforce it being civil. We have a strict no politics rule there, no Twitter outrage and no politics. As soon as I see something like that, I'm going to ban it. I haven't had to yet, which has been great. Thank you for everyone for being on the best behavior, but I'm sure inevitably some people won't be on their best behavior, and we will eliminate those people. So, unlike Twitter, you can come there and be guaranteed that you will have a much more civil experience, and if for some reason it becomes uncivil, I will step in at my earliest convenience to make sure that that gets rectified. All right. That's all I wanted to mention. There's a Pound Live channel on there for interacting with the show, so you can just use that from now on and forget about the Twitch chat. Just use that Pound Live channel, and I will scan it and answer questions from it during the stream. So there's really no need for the Twitch chat anymore if you don't like it. Or just want something a little more easy to use on your phone, you can just use the Discord Pound Live channel, and I will be watching it. So thanks everyone for making that a good place already, and I will be keeping a pretty close watch on it to make sure it remains so. All right, let's get to it. Today we've got to do some last little cleanup. I was surprised, I was thinking about how the stream went Friday night, and I was really actually surprised at how well it went. Again, I'm not a GPU guy. It's not what I spend most of my time doing. I do some GPU programming, but it's more functional and less like aggressive. So, I'm kind of the wrong person to come to if you want to know like how do you do really well optimized X on a GPU. Yeah, I don't really know, right? I don't spend my time doing that. I don't have a lot of insight to it. I just kind of know what everyone else knows, right? And so when we were looking at the fact that our multi-sample resolve was taking a long time, I didn't really know how to solve that problem, and I asked around. I was like, is there any way for me to find out if there's multiple samples in a bucket or not? And people were like, nope. Apparently on iOS you can in a limited sense, but that's pretty much the only place. So Metal is like the only thing that actually exposes that. Metal on phones is the only thing that actually exposes that. So just to give you some perspective on how limited that is. And so I was like, oh, that's a bummer. I guess we can't really speed these up. But then when we actually took a look at it, and I was like, oh, well, what if we just kept track of when we need to and when we don't need to sample from these things? Putting in those optimizations like drastically reduced the amount of time we were spending in those multi-sample resolves. So we did a great job, accidentally, right? I wasn't expecting much going into it, but we can all give ourselves a pat on the back. If you're out there right now, reach over and give yourself a pat on the back for what we were able to accomplish in the last stream, because honestly, for non-GPU people, I think we did pretty good. I'm sure that GPU people could do better, no question about that. But I think we did a pretty good job attacking a problem when, honestly, it was a pretty esoteric and weird thing we had to do, but we worked around it pretty well. I think we'll probably be able to do more in the future as we learn a little bit more about what's going on there and profile it more aggressively, but I was pretty happy with how we were able to attack that, and we sped up our depth peels as well. So I think we've done a nice job there. We've effectively got what amounts to now more or less a pretty good deferred rendering pipeline for the depth peeling stuff, because we now don't, in the depth peel part, we don't really evaluate hardly anything. We only evaluate things that actually need to get evaluated. It's not as good as a full deferred render, and the reason for that is because right now, we still, inside a single depth peel, we let the depth buffer tell us what should be there, and so we still do multiple evaluations for no reason. What that says to me is that, eventually we may want to do a little bit more of a deferred render. Since we have the depth peel, it probably is the right thing to do. rather than putting colors into those buffers, just putting an ID into those buffers that tells us what to render might be a better idea long term, because again, it would save us costly per pixel evaluations. Might be something we want to do. I don't know yet. We'll see. But that's just my guess, because as we start to layer lighting on top of this, the main thing that we're going to see is that the lighting computations will dominate our shader performance, because we don't really do anything else in our shader, right? All we do in our shader is pull from a texture and put it on the screen. We're a sprite-oriented game. We don't have a lot of complexity going on in those shaders. So it's very, very fast for us to execute our shaders. And so what's going to end up being very slow in our shaders is that lighting, because the lighting's going to have to grab from multiple sources. It's going to have to integrate those sources, and then it's going to have to produce a light reflection value. Even though that may not be a huge deal, it's going to be way more of a deal than the super simple just pull from a texture that we're doing now. And so that's really why I think we have to be aware of that and have to start to think about that shader as something that maybe needs to be deferred, just the lighting part anyway, to be deferred. And so we might do that. And the good news is for that is that all we would really need is a little bit of extra data, just a little tiny bit of extra data into the depth peel. So we would need, really just one more render target probably when we do our resolve. Would probably be sufficient to get one more render target in there. I think, I don't know, it might be complicated, we'll see. But tracking the lighting and doing the lighting at the end would probably not be too hard. All we would really need to know is what the normal is, right? Because we already know the position. So we really would only need to know what the normal is. That's the only thing we would need. And then when we do our lighting, we could do it on the depth peel itself effectively, right? And so I think we're in good shape for that. I don't love the idea of having to store the normal multi-sampled. And so the tricky thing that I think will... I'm pretty sure that what we will need to do, let's put it this way, is I'm pretty sure what we need to do is kind of store some information in a side buffer, and then what we multi-sample would have to be just a lookup into that side buffer. I'm pretty sure that's the only way we'd really be able to make it work. And then during that resolve, we would pull out of that buffer and write into our targets. Something like that is probably what we'll have to do. I don't know, but that's my guess. And so that would be a pretty big step. We'll save that to the very last thing we do, because we'll have to see how expensive that lighting actually is. But my guess is that that's going to be an issue. There's other ways to solve that problem. Obviously, we could also attack it by doing a depth pre-pass. But again, because we've got the multi-sample buffer and the multi-sample buffer is really expensive, I'm not sure we want to really do pre-passes and then have to go back over them. It's all very complicated, I know, but that's where we're at. So we could choose to do a depth pre-pass. If we did a depth pre-pass, then basically what we would do is do the multi-sample buffer as depth only, no lighting, no color, just depth. We would resolve that. We would then have our resolved buffer, and we would render once using that depth pre-pass as an equals operator to figure out what we're going to render. We could do it that way. As I say that out loud, it kind of sounds like the right answer, actually. So maybe I should take back everything I just said and said maybe that's what we will do. So that's what we want to move towards. The thing we're going to be doing today is putting our ground cover back in, and that's basically going to be about optimizing that output. I want to verify that it's the output that's taking the time and not the rendering of it, because the ways that we would address those two problems are different. So that's what we're going to be doing today, is checking out what's going on with the ground cover. I'm assuming it's just because our code that actually outputs it is not particularly well written, and then all we need to do is improve that part of the code. If that turns out not to be the case, our method of attacking it would be different. We would instead be trying to cache that ground cover and reuse it already on the card if it turns out to be a transmission bottleneck. So that's really what I want you to focus on today, that difference there. So again, a lot of talk, just trying to set the stage there. I apologize that I had to say so many things. Hopefully all those things made good sense to you. But again, we're kind of in a relatively complex space right now, and so you have to keep that in mind. All right, so looking at the screen as it stands right now, you can see we're getting a very nice frame rate here. That's because our graphics pipe is actually quite well optimized at this point, and I think we're well below any amount of time we might actually take. If we actually look here at the total time we're taking, we're actually well below even 60 frames a second amount of time used. So at 60 frames a second, we would be using 60 milliseconds. We're not even using that. And this is without even the full optimization on. We still have all of our certs in here, right? And that's with debug collation. If we actually turned off debug collation, we would get several milliseconds back. And most of that time is spent in the GPU at the moment, it looks like, as well. So we're really doing pretty good here. So that's a pretty good number. That's a pretty good number because this just goes away in our shipping version. We're sitting pretty here, I would say. And if you take a look at our frames, you can see they're mostly, again, if you look in here, you've got the game update, which is pretty reliable. You've got the frame display in here. You got the debug collation here. You can see that we get some weird offsetting. A lot of what that is, I think, is the unreliability of whether or not we hit or miss the Windows display stuff, which is kind of out of our hands with the weird setup we're using right now, which has to go to the HDMI as well as the monitor and stuff like that. At some point, I should probably get a splitter so we don't have this problem. But anyway, that's what we're looking at right now, and that's all fine. So I think we're in good shape. But what we're going to do now is take a look at what happens to these timings once we put in that ground cover. So, you know, if we take a look at the actual entity output right now, there's kind of a crappy routine we threw in there for outputting ground cover. You can see right here during fill unpacked entity, we put that ground cover in, but we never actually render it. And you can see that the reason we don't render it is... Actually, I'm right in thinking that does get called, right? Yeah. Is because I believe there's a separate function, there it is, called draw ground cover, which when we encounter an entity, we are spooling out to this function to take the ground cover that's specified as being on that entity, and we're dumping it to the graphics card by putting it into the buffer. You can see here what happens is we look at what bitmaps are used for any particular piece of ground cover, and we push a sprite out for that. And what happens if we turn this on, so I'm just going to turn it on here and you can look at what happens in the game when we do so, is that once we turn that on, you can see that we have a 17% hit here for render ground cover, and you can see that our timing does jump up dramatically, right? So we get a much worse performance profile when we dump a ton of ground cover in there, which is what I've just done. So if we draw out, if we pull back a little bit here, what you can see is you've got all of this ground cover that we've spammed out there. And my question, the first thing that I wanted to ask, as I was saying before, my question I want answered is, to what extent is the ground cover based on the rendering, right? Like, to what extent is it based on the GPU? Is that what's causing us to be costly here? Or is it the fact that we're taking too long to actually push it out, right? And so if we go back to our frame display here, you can see that here. You can see here we got the debug collation and the frame display. I'm going to go over here to the game update. And in game update and render, what you can see here is we've kind of got a breakdown. Begin world change, lighting test, right? These things are not really taking any time because they're, this one doesn't do anything and this one's not really operational at the moment. We jump in here, and there's too many things counted in there. Looks like we need bigger vertex buffers. Maybe I should maybe I should update how big those vertex buffers actually are. Hold on a second. Of course, the problem is this is not a very fair test because the debug collation would show those differently, but man, let's hold that thought. So if we were to give ourselves more space, like this is much more than we need for actually running, obviously, but if we were to give ourselves more space so we can output lots of little things to the debug system, let's go ahead and take a look here at where that vertex buffer actually gets allocated. Oops. So we should have some render limits here. You can see, let's see where that's coming in here. So here's our limits. Max quad count per frame. That's pretty much what's going to do it, right? And so I can update that a little bit. We'll see. It might be getting a bit large at this point. But if I give ourselves a much larger vertex buffer, we should then be able to output something larger, right? I would think. All right. So again, drilling down to the game update, I just want to look at the entities. It looks like that, for whatever reason, it looks like that's just outputting too many things. But I don't know why. Are we counting way too many things somewhere here? I might be misinterpreting that error. We should find out what... It's saying that we're out of space to submit that to the graphics card. But I'm not sure why that would be. So I'm wondering how we're ending up with so many calls. You know what? We should be able to look at... We should be able to see that pretty easily in here, right? Why do I keep looking at the memory? So I guess it's because of stuff like this. Render ground cover is getting called that many times. Maybe what we should do is just take a look at that as being something that doesn't get opened and closed as many times. But yeah, if you look here, you've got so many of these things opened every time. I can see why that's too many, right? I mean, that is just tens of thousands of those zones. And it would be nice to not actually do that. It would be nice if we didn't have to open actual zones for that. We just did a summation. But yeah, at the moment, maybe that's a little bit hard to do. So yeah, if you look in here, the way that we're timing it, just not great, right? And we could time it a little bit differently, like, and so on. I'm going to get rid of things like timing each of these individually for now. And we can open that back up again if one of them starts to be a particular problem, right? But let's just get rid of those for now. Because we're counting them for every entity and it's just not constructive, right? So if I was to actually get rid of all of those, right? And we just looked at update and rendered entities by itself. That should take a lot more stress off of that debug system in terms of how many things it has to collate every frame, which of course would be good. And so anyway, if I go in and look at the frames now, and in fact you can see that, right? You can see the debug collation got a lot cheaper, right? And the reason for that is because we're not dumping, you know, tens of thousands of zones into it every frame that it has to account for. So you look up now, you can see that mostly this thing is the only thing that's really getting pounded on, get best match asset from. We do need to start looking at that a little bit more. Remove world chunks, pretty modest. And so that should make it a lot easier to drill down here and see these things without too much fuss, I would think. Wow, still not. So I think this must be a bug. How is it? It doesn't seem like it would really be possible that we're getting this error here. Let's take a look and see. Can we look at commands at all? No, we can't. Let me take a look at what's going on there. That just bothers me. At this point, we should be able... I mean, with that much vertex space, something's up. So I think we just got a bug or something. Let's go exploring. I want to know what's going on there. I don't like that. Hitting that headroom doesn't make a lot of sense to me. Not sure why that would be happening. So here we are running the debug. Obviously, that costs a lot more. Let's take a look. Oops. Let's take a look at the frame display. You can see now all this stuff got a lot slower, as you would expect, because it's all debug compiled now. If I hop into update and render world here, this is the place we were getting the crash before when I click on this. So when I try to open up update and render entities, we get this nasty error hitting us. The question is why, right? So let's inspect what's actually happening. Maybe it's an erroneous assumption that I'm making about who's causing this problem. Maybe we just have a bug and we can fix the bug and then not have this problem, right? So what you can see here is we're getting a bug inside draw frame bar graph, and that is what we would expect to see in the case where we would draw too many things. So, you know, it's not looking good because it looks like it is actually something where we're just drawing too many of these. And I don't know exactly how many of them we've drawn, but let's take a look inside where we're actually erroring out and see what the command table says, right? So if we take a look at our max vertex count and our vertex count, we are actually syncing 4 million vertices in this case. And that's just way too many, as you might expect, right? So why we're syncing that many is hard to say, but I guess it's because we have 256 frames to display. And in those 256, let's just do the math, right? We were doing about 2,000 of these things. If you look at 512, the number of vertices we were syncing for those is probably going to be like at least 6, but probably more like 12. There's our 4 million right there. So you can see that that frame display is just way too costly for us, unfortunately, just again because of how many it draws when you start to have too many zones piling up like that, right? And so if we take a look inside the asset query there, that was the thing that was really hurting us, right? The thing that was saying we got to do, this is how many, this right here, get best match bitmap from, right? And so what we kind of need, you know, in the best of all possible worlds, and maybe we should do this at some point, but we kind of need a way of timing zones that doesn't incur such a bad overhead, right? And we don't really have a way of doing that at the moment, but maybe just things that do general sums that don't create as much work for us in that sense. You know, maybe that's the best way to do it. I don't know. But you can see that basically our problem is this right here. Because that's the last thing that gets called way too many times, right? But it's difficult to say because, you know, it means that we don't get much insight now. So now we're probably fine. In fact, I can probably switch off of this. But it looks like there was no bug. It's just really too much data to display for how much space we actually allocated for ourselves. I don't know how to work around that problem. I'm not sure what to do about that. You know, one way is just to make a much bigger vertex buffer in debug mode. I don't really know. It's a tough one. It's a tough call. Anyway, if I look at the frames now, presumably the bug should be gone. But of course, we also have the problem that now we don't get any visibility, right? So it's kind of an issue in that regard, because what we would like to do is we would like to be able to have our cake and eat it too, right? We'd like to be able to see inside here, you know, what's taking up the time. So, you know, 6 of one, half dozen of the other, but at least now we can sort of also say, look, if we take a look at update and render entities, we can see how much time it's taking. We can take a look at the differential of that, and if we do the ground cover, and we can probably do one better than that, which is to say that, look, iterating over the entities is probably not the worst thing in the world. So if we wanted to, we could probably also do something where we draw the ground cover after, right? So like in theory, right, if you wanted to, you could do something like this, where you do like a second pass afterward and draw the ground cover there, just for purposes of easy timing, so you can know that you're not timing like the function call overhead or something like that. That would be a pretty easy thing to do as well. And so if we take a look in, say, here and look at how the ground cover was getting output, we just take a look at how that's working. Draw ground cover. You can see here that there's really not much information that it needs. And so if we wanted to, we could just get rid of that, right, like this. And then in here just say, all right, why don't you go ahead and draw that, right? So that is one solution to the problem. And if we want to solve the problem that way, then we can, at our discretion, make the begin and end block situation here a little more concrete. So what I could say is, instead of this update and render entities timed function here, what I could say is like, okay, let's do a begin block, end block around just this part here and see how bad it is. So let's do begin block, draw ground cover, end block, like that. I think that's all we need to do, right? Is that it? And now it'll only get called once, and we can actually see it without stressing the debug system. We can, you know, see it pretty clearly, right? So if you take a look now at what we're looking at, and you don't have the function call overhead in there of calling it every time, then we can see a more pure estimate of the cost of just doing draw ground cover. You can see it's bad, right? So I don't know if it's the only cause of badness, but it's a significant cause of badness, right? And if we were to go look at what's happening to our frame times strictly on the GPU side of things, we could get another clue as to whether or not this is really an issue, right? Let me go ahead and load this up in RenderDoc. I'm going to launch. Here's our frame. I'm going to capture that frame. And then I'm going to ask it for the, kind of bogus timings, but at least give us a little bit of proportion. And what you can see here is that while it does cost more to draw these things because there's a lot more going on in them, it's not the end of the world, right? These numbers are not so huge. They're not even in the thousands, a lot of these, which is what we were paying before just for the multi-sample resolve. So honestly, and if you look at the smallest of them, remember each of these has to process all of that ground cover. It's still not even up to a millisecond of time for each pass that has to process all of them. So it looks to me like the GPU is never really struggling particularly hard on this level of vertex throughput down the PCI pipe. So it doesn't look to me like I'm too stressed about it in general, right? So what that suggests to me is that this is the problem, not just how much we're drawing. That's what I thought was true, and it's what I hoped was true. Because it's much easier for us to optimize this than it is to optimize the other part of the process, right? All right. So taking a look at draw ground cover, the first thing that I want to know is which part of it is slow, right? So I want to know whether this is causing us a problem or whether this is causing us a problem, this get bitmap call. And if you take a look at the get bitmap call, it gives us a little bit of insight into what's happening. You can see here that what we're doing is we're checking when we call this get asset, right? Let's take a look at that. You can see it just like doing a direct reference here. But you can see that what's happening is if it's valid, we do a little bit of work on it, and if it's not, we don't. The question is, how much does this cost? How much does this cost? How much does this cost? This cost? This cost, right? There's a bunch of things we're doing here, and I don't know which ones are costing us the time. So what I'd like to know is a little bit more about that process and whether or not we should be worried about it, right? So here's the first thing I want to do. I would like to remove the calculation portion. And because that's an easy thing for me to remove, I'd like to remove the calculation part of the process and enable myself to just do a simple like block copy of the data that I actually need. So for example, if I take a look at push sprite, what you'll see about push sprite is it's incredibly expensive, all of the crap that's going on here. First we have to do this, then we have to compute this, then we have to do all of this nonsense, right? It's a lot of garbage. There's just a lot of garbage going on there. Look at push quad. Oops. Here's push quad, right? Look at all this crap. I mean, look at everything that that's doing, right? There's just a phenomenal amount of work going on in here. Just a phenomenal amount of work, right? Way, way, way too much. And so if you take a look at what's going on there, my inclination, my first thought, is maybe all we really need to do is just compute this stuff first and cache it, right? Because if I could do that, if I could compute this stuff first and just cache the information, then all I really need to do is just block copy this, right? These indices and these vertices. These I can write out fresh every time because they're trivial, right? These, which cost everything, that all the cost was in here, I just save the values, block copy those for our vertices in. That would save 90% of the CPU work that's happening here. Would that be enough to get us out of the danger zone and into a happier space, right? I don't know, but again, that's my first inclination. So what I would like to do is say, let's start to attack that problem. There's two ways I can attack it. One is I can try to separately profile the cost of doing the computation versus doing the other part of the process, right? The problem is that's a little bit difficult because it would require me to somehow be able to time these things in a more fine-grained manner. Now, I can try to do that, right? If I look at get bitmap info, I can see that like it's just kind of a lookup, right, in this process. So I don't think that should be too bad. So if I wanted to, I could basically say, look, let's split this off and just say this is the computation. It's not great because now there's overhead getting counted against the outer routine. But at least it would give me some idea if my suspicion is correct before I go spend time trying to solve the problem. So now if we take a look at what's going on, what you can see here is that the draw ground cover function itself doesn't seem to be taking very much time, right? I don't know if you can see that there. It's only hovering around 5%. Whereas the function that's actually, I'm sorry, the part that's actually eating all the time, that computation, let me pause so it's not flickering for you. You can see here that the 20% of the entire frame time is spent just doing just that computation. This is probably even much less because the overhead of getting these blocks started, 44,000 of them, is counted against ground cover in this case. And so this is probably even less when you take that out of it. So I do think that computation, I think it's safe for me, without going out on too much of a limb, it's safe for me to say, look, that computation is really bad. How do we address it, right? Okay, so let's try to start addressing it slowly. Okay, so let's suppose that I was to go over to the place where we're storing these actual entities. So we go look here, and what you can see is that our entities kind of have a ground cover thing here, and it's this entity max ground cover nonsense, right? And the question is, what's going on with that, right? And so if we take a look at the ground cover, the way that that works, it's basically a bitmap, a position, a color, and a scale. And we're using that, we're like decompressing that every time basically to produce, you know, this information. Now what I would rather do is I would rather figure out a way of storing the ground cover in the form that it's directly, like how it's directly used. That'll take up more space in my entity, for sure. But there's ways of getting around that, and we already have a caching system that means that when we can add arbitrarily large stuff to our entities, and we only pay for that for the entities that are actually active at any given time. We don't actually pay that cost for the potentially millions of entities we could have in the world because they are not in the cache. So it's not that bad to make our entities fat because we've already done the work to make sure that they stay lean in the bad case where there's, you know, millions and millions or billions of them. So when we take a look at the ground cover here, what I want to do is see what can I change about this process. Well, looking at the render itself, we get an idea for what we actually output to these vertices, right? I actually remember where we've placed that. There it is. So here's our textured vertex, right? And you can see we've got the information here for each vertex stored. It's a little bit large. It's got a p-value, an n-value, UV, and color. Then it's got a texture, an emission, and a reserved, right? So it's a bit large if you look at how big it actually is. It's a bit large. And if we think about how big it is compared to one of these, let's just count it up, right? So it's two, effectively, if we count this U32 with this V4 here, we've got two V4s, or two 4x4s, right? So that's 8x4. Let's jump over to speed calc. So we know, just to make that explicit, we've got, in fact, I can just write it out regular. We've got a 4 times 4, plus a 3 times 4, plus a 2 times 4, plus a 4, single 4, plus a 2, plus a 1, plus a 1. That's our total size. So a textured vertex is 44. We know we need 4 of those. So this is the entire size we would be taking, 176. We would take that per ground cover element. Now what we were storing over here was a bitmap ID, which is 4 long, a 3 times 4, a 3 times 4, and a 4. That's only 32. And so we will be exacerbating the problem of the storage by blowing it out. No question about that. But we have to ask ourselves, how much of this do we actually need? Because to a large extent, we probably don't actually need to store all of this. A lot of it is redundant. Now what we do know is the normal, probably going to be the same. Texture index, probably going to be the same. Emission, probably going to be the same. Reserved, probably going to be the same, or nothing, right? Color, probably going to be the same. So when we look at what we actually had to do computation on, it's mostly P and UV, right? So my thinking is we can probably get this down to per ground cover, actually storing something much more simple, right? We probably don't need to store it times 4 for all of these things. We can probably get away with our times 4 only being the P plus the UV, which is 6 times 4 times 4, or 96. That's a lot less of an increase than we would have been suffering otherwise. And for all I know, we don't really need to store that completely either, because we might be able to store a quicker way of getting that produced. So when we go to look at it, we really do have options for keeping this more under control. So I think we're going to be okay. Let's take a more worst case approach to it at the moment and say that this ground cover that's getting generated in here, let's maybe say we want this to be a little more straightforward. And so instead of storing the things exactly as we were, we're going to store them a little bit differently. First of all, we will pre-pack our color. That's something that we can do pretty easily. That gets us out of the business of having to take this V3 color in there, and it takes less space anyway, so it's just a good idea to begin with. Then we know we've got these P values in here that those are the things that are probably pretty expensive to compute. So at the very least, let's store the 4 P values that we're actually going to use instead of just some value that we used to create them, which was P plus scale. That was how we were creating them before. And then we'll maybe take the normal and say the normal is going to be constant, so we're probably not going to do anything with that. We're just going to stuff that normally. And similarly, the texture index is something that's going to come from the bitmap, so that's probably something we can't really work around at the immediate moment, although maybe some things we can do to make that be a little bit better in the future, but either way. So these are sort of the constants. These are the things that are constant across all vertices. These are the things that change per vertex of output. Same thing with things like emission. That's probably something we can also put in there, right? So this emission value can probably be stored. And we probably store some other things as well. So the only question now is, what do we need to store for UV? My guess is we don't really need to store much for UV because probably we're just going to have a 0 value for the base of the UV. So my suspicion is we actually only need 1 UV value as well, which is how it stretches out along the texture. So I think we're really going to be able to get away with going from this. So previously, let me make this a little more explicit. I think we can get away with something like that. So I think we can go from something that was storing this to something that was storing this. I don't think that's a huge deal. Let's do the comparison just so we have a little bit of perspective on the subject. If we take a look at how much that costs, we've got a 3 times 4, right? 3 floats for the V3, 3 floats for the color, and then 1 float, right, for the scale. So that's a 28 was how much that cost. We then have 4 bytes for the U32, 3 times 4 for the N, and we weren't storing that N before, so I don't know, but we were kind of generating it, so maybe that counts. So you have 4 plus 3 times 4, then we've got our UV, which is 2 times 4, we've got our emission, which is just 1 byte, and then we've got our P4, which is going to be 4 times 3, right? 73. Now this probably should be stuck at the end. I don't know if we really need emission because ground cover doesn't have emission, so maybe we'll get rid of that and just say it's 72. 72 times divided by 28. We're making it about 2.5 times larger That, again, not the end of the world. I'm not going to lose sleep over that, certainly not in this part of the code anyway. So I think we're okay there, and this would allow us to generate the ground cover much more quickly. Why would it allow us to do that? Well, if we now pop back to the entity system and look at what was actually going on, if we assume now that we're taking a look at this draw ground cover function, and we're looking at what we would have to do in order to output our sprite, we can pretty much say that this is an if0 around here now, and we can do an else call. This is stuff we're going to do in the code where we generate the ground cover, which, remember, is much cheaper because it only happens when an entity comes into the cache. So we pay that cost only as entities come into the cache, which happens like at a slower rate, right? And not only does it happen at a slower rate, but we can manage it if we needed to. We could trickle charge it if we want to. So basically, if too many entities entered in one frame, we could trickle them out over a course of frames because they tend to move in on the apron, right? Not all into the view at once. And so we could also, help mitigate some of that issue by putting in flow control or rate control to avoid having too much of a hiccup on any given frame. So I think we also have a lot of options there in addition to it, right? So I think it's going to be easy to mitigate that problem. So that's what we're trying to do. We're trying to move code from something that has to happen in every frame to something that only has to happen when entities change their active set. So here we go. If we now want to write a quad out here, essentially what we need is a push magical quad or something, right? We need some function that allows us to push our quads out cleanly. And we don't really have a way of doing that right now, unfortunately, but that's something that we need to be able to fix. And so if I was to go to push quad, what you can see in the push quad code here, right here anyway, right? You can see it getting this sort of quad stuff out and doing a bunch of garbage here, looking at special textures, all this sort of stuff, right? This is precisely the stuff that we want to avoid. We don't want to have to do any of this stuff. We want this to be a lot simpler, and that's part of the rendering optimization, is taking code that was just written to do whatever because it's whatever we thought of at the time and it's just the easiest thing to do, which again you always do want to do because you don't want to make matters complicated for yourself until you know what actually costs you the time and what actually is important. So certainly not an issue. I'm not blaming past us for doing anything wrong. We didn't. But when it does come time to start thinking about how you're going to streamline that process, now is the time to start looking at that. And so what I want to do here is I want to create a good way for me to effectively do this, right? So I want my code here to be able to do this, right? And what I want to be able to do is at the outset, since I know how much ground cover we have, I want to effectively be able to make a call that's like, I'm going to push this many vertices on. So this is going to be like indexed vertex output or something like that, right? I want to be able to make a call which is like output quads. And I want it to be raw. So I just say, look, I'm going to output this many quads. Give me back the information that I need to do that, please, right? And so then what I want to do is say, okay, I've got, this output function that should allow me to do this very cleanly. And now I'm just going to push vertices on it. So I'm just going to do like a push vertex here. And I want to be able to put on these pieces of information, right? Okay, so first things first, we need to be able to figure out what these p-values are. Well, guess what? We're saying we're computing those ahead of time. So that's going to be easy, right? So our p-value is very simple. It's just whatever the ground cover said it was, right? Our n value is also simple because it's stored in there. Our UV is a little more complicated because as you can see, we have like a bunch of UVs that get pushed in here and we don't really know what they should be, right? So that's a little bit harder. So we effectively have some set of UVs that we're going to have to work with, and maybe we'll keep the naming the same as they were inside our quads or something like this. So I don't know what we'll do with that. We'll talk about that in 1 second, but we're going to push on a UV there, right? And then finally, we're going to have in our, we're going to have a color value, so this can be modulated. We're going to have a color value, and we've already specified what that color value is as well. Oops. Didn't mean to make that cover. And so we're going to have a color value there, which specifies what the color is for our vertex. Texture index, we don't know what it is yet, so we're going to have to push that. But then we're done, right? That's all the things we need. Okay. So now we just do this for every vertex that we have, right? And so you can look here. Actually, I guess the way this was doing is the P3 was pushed first. I don't know that we really want this to be doing that weird winding, so maybe we'll just do it this way, right? We'll start to clean this up a little bit and not do it the way it was being done before. So we'll do something like this, right? And that will be sort of the clean way of putting those vertices in place, right? Now, there is something a little bit unnecessary about this, something I don't super like, and I don't really know what the compiler is going to do with it. And so I'm just going to mention that we sort of have an issue here. The issue that we have is I don't know what the compiler is going to do about indexing off of the pointer. Let me just explain to you what I mean by that, and because it's kind of a little bit relevant. So inside your CPU, right, it's got a bunch of logic in it that deals with memory. And the way that it uses this logic is that it has special purpose routines hard-coded directly into the arithmetic logic units. Well, they're not really into the arithmetic unit. They're into a special unit that's made for memory, but that's neither here nor there. It has special circuitry that's designed just to do things like array offsets, right? And so there's two things that your CPU can do at any given time if it wants to access memory. One is it can, like, you know, take a register, like a pointer, right, and say, get memory at pointer, right? It can, like, do that. Or store memory at pointer, right? That's the thing it can do. And that kind of a thing is just called a mov instruction usually. So you'll see things like mov, and it'll say, oh, I want to take some particular pointer. So there's a register, you know, register with pointer. It'll take some register with a pointer, and it'll move something there. And then it says, like, well, what did you want to move there? And it'll be like this floating point value, right? So some register with a value. So you can do stuff like that, right? And that's like the bread and butter of how you move things off to where a pointer is. But you can also do things like this. And this operation is free. It costs you nothing to do. It's 100% free, basically. That's probably an overstatement, but it's almost free. However, this is not free. So if you take a look at what these two things, what the difference is between these two things, one code set looks like this, another code set looks like this, right? These two things do not cost the same. This one is cheaper than this one is. And the reason that this one is cheaper than this one is because the CPU can do that plus 12 for free. And so the compiler, in many cases, is smart enough to look at your usage pattern and know when it can do offsets. So if you tell it something like this, inside a loop, it's often smart enough to do this. Right? So I'm ignoring the values here, but point being, it's often smart enough to say, oh, they're just writing to sequential locations in this loop. So I can just use hard-coded offsets because they're a size that I know. I know what this is pointing to, let's say, right? And then I only need to do one add at the end of the loop to move the pointer up by the total number that I've written. So it's often smart enough to aggregate those two things for you. But this is what you wanted, and this is not, right? That's the way to think of it. I did want this, I did not want that, right? And there's a lot of complexity here because actually, right, literally this and this, it doesn't matter which one you choose. Because of the way the CPU actually executes with ports, it's probably the case that this is no more expensive than this, and there's a lot of other things we could talk about that have to do with that. But once you start adding way more of these mobs on there and so on, you start to get into a situation where it does actually matter and so on. And so you want to make it easy for the compiler to output this and not this, right? And so sometimes when I'm down in here in the nitty-gritty and I'm thinking about how to output stuff quickly and I want the compiler to output the correct set of code for something, I will intentionally make life a little bit harder for me and write this rather than this, just because I want it to be really easy for the compiler to see what I'm doing. Maybe I'll just do that. All right. So again, I'm just trying to give you some perspective here on what I'm doing. But I may want our fast output. Maybe I'll call it out vertex, something like that. Or vertex out. So I may want it to look more like this, where we do a bunch of these, as many as you want to do, and then once they're out, you do an advance, right? Something like that. Rather than just letting this increment the pointer. So that way it gets incremented only once at the end of a quad output, rather than something a little bit more granular. And again, the reason for that is so that you can have more control over what's going on there. That's like the goal, right? And so here we would basically say, look, the index out is just going to be, you know, draw these things in order or whatever, right? And I'm going to use a basis value for that as well, just so I can make sure that we can also make those be striated if we want to produce more indices than one at a given time. But that's more what I want to see when I look at that. That's like sort of more what I'm looking. That's more what I'm looking for, right? So I want to see something like this. This is what I want to make, and that way I can stream these vertices out really aggressively and not have to worry about how much time it takes. Because I know the CPU code will be like very well optimized in that case. And the slow part will now be this garbage here, which maybe we try to optimize in some way, or maybe we don't if it just doesn't matter that much, right? Okay. So that's what I'd like to do. It's pretty easy for me to write this, and I will. But then we need to look at the opposite side of this, which is that this code here still needs to happen, and it needs to come from somewhere. So this texture index here, I need a way of getting that texture index. If I go look at the push quad call, right, I should be able to see how we were getting it in here. You can see here we do texture index from this texture. So I should be able to do something like that. I believe sprite values for upright is probably the thing that's doing that right now. But if you take a look at how this is happening, right, it's just doing this downcast here. And all that should be good. So I probably want something that converts this for me, probably something that looks like this. Something like this. I think I probably want a like non-special. In fact, you know, I'm looking at this. Why do we even have to, like, shouldn't this just return a 16-bit value? Hold on a second. Yeah, I mean, I feel like this should just return a 16-bit value. The texture special bit, I feel like this should really just be returning a 16-bit value to begin with. Probably. I mean, technically, if you, it's really whether or not you know. So well, we'll just do it this way. So we're going to go ahead and grab out this, and we're going to make sure that it's the 16-bit index as we go, but that's pretty much all we needed to do. And so then we can just output this stuff, and really now our goal is to move this code that we have here, right? We're going to try and move this code sort of out, right? And don't ask me why I did that. I didn't mean to. And so let's go take a look at where that code goes and how we're going to adjust that code. So taking a look at this streaming out, that all looks like fine to me. You can see how much simpler that is. No function calls, just really streamlined. It's just a bunch of block copies. These are just going to be inline function that just block copy that data in order. And the only reason I'm not doing that manually is because that makes it easier for me to change the vertex format and know who's using it where, right? Okay. So when we go fill our ground cover up here, you can see us doing it like this. When we actually produce this sort of information and do our kind of like work to get our best match bitmaps, basically what I want to do is not fill in this stuff this way. I want to fill it in this way, and we kind of have some work to do because this information is now stuff that, you know, we want to kind of capture, right? We want to kind of get this information out in a different way. So we're going to do that in a second. Okay. And looking at this, right, this can still, the cover bitmap can still be written out that way, but the other stuff needs to be written out differently. So let's just go ahead and take a look at all of the parts that we have here, and let's make sure that we're writing out all of them. So now we do have a color, much like we had here, but we want to kind of make this color be something that someone could set, like later on when they're trying to do like variant color, like maybe there's a randomization of the color, whatever, they set it as a V3. Then what we want to do is pack that back up, right? So we want to do like a pack of the RGB. I don't remember where this is. In fact, I'm not even going to try and remember. What I'm going to do instead is just take a look at how this was doing this here, right? You can see on push bright, that's probably where we're doing it. In fact, you can see it right here. We have an RGB pack 4x8, and we do the premul on there, right? Like this. So you can see this process here that we're doing with the store color. I don't love the way we're doing this exactly. It's a little bit annoying when we look at how that's supposed to happen. I kind of feel like that should be a little bit more straightforward. And so I think what I want to do is maybe change the way the store color is working to be sort of an all-in-one call. So the way store color works currently, it just does the premul there for us. I think what I want to do here is make our own function that's more like finalize color, something like that. And so we take the input here or like unpremultiplied. We pass that through store color, and then we pack it down, right? And again, that's what this is doing. Again, what I'm trying to do here is nothing fancy, right? Nothing weird is going on here. I'm just trying to make a systemic way that everyone who ever does this can just call this function and know that no matter what random, crazy way that people are using color stuff, I just want there to be a way they know they can just call this with a normal non-premultiplied color, and crap will happen, and you'll get back the right U32, right? So that way, nobody on the outside is thinking about how colors are encoded. They don't care. They just need to know that they can pass it through finalized color, and they'll get the right answer. And that's all they need to know, which is good. Because I don't want people to have to know, because what if I change it later, right? Because it's a bunch of hairy crap that has to happen, and maybe I want it different, right? So the finalized color is just going to be done this way, like that. And then anyone can call that with the color that they generated and know that it gets packed down properly. That's all we need to do for that. For the normals, we're not really doing lighting yet, so it's kind of difficult to say what the lighting should be. But for the most part, I think these things are things that are supposed to be sort of front-facing. So I suspect the normal for our intentions at this point are going to be things probably like that. But we don't really know. So I'm going to put a to-do in here and say, you know, adjust this once lighting is, you know, working. Once we're actually lighting sprites, we'll see what that has to be. Right? Okay. So then we've got the UV and the P values. That's really most of what we actually have to do now, is compute where these P values should actually go. And we know we have a point from UVW thing happening in the collision volume here that gives us the base P, but we don't know what to do after that, right? So now we've got a bunch of crap that has to happen here. You can see it happening here, and we probably still need to do this stuff. But then we kind of want our sprite values for upright call to be the last thing we do. We don't want to push the sprite on, so we want to generate all the rest of the stuff that this thing would have done. We want to generate that ourselves. So that push sprite call is kind of now something that's a little bit suspicious. We don't really love it. What we would like to do is take that code and use our own computations to do something smart there. And by the way, we can make this a little bit more optimized as well by calling finalized color, not optimized, cleaner, less work to maintain, by reusing that code that we were using before and doing this. That way we know that those are both going through the same path now, and there's not multiple people sort of falling over themselves doing weird store color antics. So anyway, in here now, you can see this does these operations, right? You can see how it's unpacking that. And what we'd like to do is make that push sprite, again, I want that to be something that now can work better with faster flowing code. Now, one of the things that you'll notice is that it's really not doing much with the other pieces of the code, right? It's mostly just computing the P and the UV values. If you look in there, what it's doing, it's computing P values and UV values, but everything else is a pass-through. The texture is a pass-through. The normals are not even mentioned. The color is a pass-through. It's just the P and UV values. So again, I think we can take a step backwards here and say, let's make this push sprite call be even more amenable to pre-calculation. So if we take a look at that compute, what was it called? Compute sprite values or sprite values for upright, that, I don't even remember, this thing, right? So if you take a look at one of these things, we've got these sprite values here. Let's go ahead and make there be a thing called quad values or something like that. That's the equivalent of it, and let's get this stuff out of there. So let's get these up in here, right? So we got a P4 there, right? And then let's get that UV working so you can see how this thing gets output, right? The min, max, right? That nonsense. You can see that getting passed down here, right? Let's make that be something that, well, and you know what? Now that I'm looking at it, just even looking at that, I think for the most part, that doesn't need to really be there either, right? It's mostly just this is the calculation, and this other stuff is just exactly what you would have expected it to be. And so, yeah, let's not worry about that at the moment. So if this right here is getting done with this quad values thing, then we know that we don't have to compute that anymore. That can just be generated directly off the sprite values. And similarly, these things for all these UVs, those could be generated directly off the sprite values as well, but those are so rote at that point. I'm just not sure we even want to store those, because you can see that the min and the max UV, and that min UV is probably 0 most of the time as well, so that even that is kind of absurd, the way that that's working. So just, again, trying to step back a little bit from how this is happening and make this be a little bit more systemic. I'm not sure. I'm going to go ahead and push forward a little bit on just making this be custom. So I'm going to do this here instead. So you take a look at what we're actually passing down here. This is the min p value, right? So that's the min p. The scaled x-axis and scaled y-axis are just the things that came out of Sprite, right? So these are these. See them. So that's fine. And then the rest of this stuff is irrelevant, right? So here are the p-values we actually would be writing. So you can see us like write those directly out this way if we want. We can just, you know, get rid of the middleman here. And again, those p-values there, they don't actually need, because we're not using that z-bias anymore, we can really actually get rid of the z-bias entirely from our system at this point, because I don't think we actually ever need it. Since we can get rid of that z-bias now, I think that means that basically this can just be written this way, because we don't actually need to store 4-element stuff. We're not using it, and it'll probably just go away. So we can pretty much get rid of all the notion of the v4 in there and leave it like this, right? So that leaves us with just the UV, right? That's all we actually need here is just the UV at that point. And so now the only question I have is, what's the most efficient way to encode that UV? And so if we go into push quad, remember push quad is the thing that's actually doing the work for the UV. And you can see what it does here is it takes the input UVs and it actually does the mapping to figure out how those things exist based on the texture size. So I don't know if you can see that happening here, right? But you can see as it goes to get this inverse UV, right? You can see that being calculated here. And so that's something that we want to, again, similarly make systemic based on the texture. We know that this is never going to be a rectangular texture. We're not using rectangular textures in our fast path. They're just for cutscenes. So we know that we really don't need to do any switches. We don't need to test to see what's going on here. So what we want to do is in here where we go in and set this UV scaling value basically, is all we really want to know is what is this? We just need to know what this is going to be versus the, where is it here? Versus the texture width and height, which we already have. So that's really all we need, right? That's really all we need. And so if we assume that the ground cover always draws the complete thing, which we don't actually know, so we may have to adjust this later and have 2 UVs, like a min and a max, right? If we want to pull out of chunks of a thing, for example. But assuming we don't want to do that, then all we really need here is to just say, look, all right, we need you to do, we need to compute this thing, right? So we need that value there. And we could make that be something that's, again, systemic in a way that lets us do that easily. So basically get scaled texture coordinates or something like this. Or scale UV to texture, right? And all you need to do there is just do this. So I guess we don't want to call scale U. We just want to do like get UV scale for texture. It's probably the right way to do it. That's better. And so in this case, you have to pass the texture, but that's all you need to pass. And we probably want to specify like regular texture, because it doesn't work if the texture is special. So in here we just say, all right, we've got our inverse UV. That's going to be true for any time you use this particular texture. Render texture, right? And so we're going to return the result like so, right? So that goes ahead and gives us back this in a reliable way that anyone can now use. So you get UV scale for regular texture is all we need there. That can then be called here, get UV scale for regular texture, and that's actually all we need to store, right? So for whatever this texture actually was that we ended up using, that's the thing we need to store the scale for, right? Now we didn't actually grab the texture, so we need to grab the texture and get that piece of information out of it. So this here, if we didn't actually load it yet, we can't actually get that piece of information. The bummer drag about that is that we kind of need it, right? But the good news is we should be able to do this without loading the texture, right? In here, if we looked at what the bitmap was, that would tell us the scale, right? So in theory, even if we haven't loaded it yet, we should be able to do this the other way around. We should be able to make a call that's something like this, right? Or maybe even that. Where we just say, look, we got the bitmap info, compute the scale using that. Because that's what you actually needed. You just need the texture, width, and height. You know what those are going to be once you see the bitmap info. We don't have to actually have the thing paged into memory to do all the work, which is what we want, because when I create this, I don't care if it's loaded into memory. I'm not going to draw it. So we should let the background loading routines have way more time than this. They shouldn't have to be pressured in that way. So what I want here is a way to get this information without knowing what the actual texture is. So let's implement that as well. If you have an HHA bitmap, again, inside the renderer, it's basically this exact call, which is get UV scale for bitmap. And there's a bitmap info, right? And that bitmap, what's it called? HHA bitmap, sorry. So there's the info, right? And if I look at HHA bitmap, I can see that in here I've got a dim and an org dim. I have the information that I actually want. When I stored the bitmap, I know what's actually going on, right? And so when I look at, for example, when we submit these textures, so inside load bitmap, right? What we actually do is we use that width and height to see what's up, right? We see what's going on there. So if I wanted to, I could do this. I don't know why we have to pass the assets for that. Do we know why? I do not know why that's being passed there. Possibly because of this. But I don't love that because I'm not sure why you would need the assets there. So I'm going to eliminate that for now. And in the future, we can put it back in if we really need it. But I don't really want to do that. So in here, I can say, look, if you needed this, then we do one thing, otherwise we do the other thing, but we'll always produce the right result for you either way, right? We'll always produce the correct value no matter what. And so if we do get UV scale for bitmap, and really if you look at this, we don't even need that. We just need the dim for it, right? We just need you to tell us like what it is, right? So we really just need like that is all we really needed you to tell us, and then we can compute the value. So in here where we do dimension cross special texture, we can pass the width and height. If they do, then the UV scale is just nothing, right? I think it's just 1, 1, but I'll go double check that that's true. And so really we only have this case where we need to know if this thing doesn't require a special texture, if the texture is effectively regular. Then what we want to do is compute these two values. So we want to compute the x value as being the width divided by that texture array dimension. And then in, same thing here, like so. and off we go. Now, again, I don't know whether or not we want this thing. Probably the reason, and you know, I could keep this going. It doesn't really matter, right? If we wanted to make it this way, we're just protecting ourselves effectively for needing to make that dynamic, this value, so we would look it up inside the assets. Maybe we want to keep that. I don't know. I'm willing to say that we might. And it's pretty easy for me to pass it around. So, sure, right? Whatever. If you go back and look in here, you can see that that is, in fact, what we do. You can see us doing the 1.0 in there, so that's all fine. So this basically gives us the thing that we needed when we're actually calling this in the entity output. So here, where I'm doing get UV scale for bitmap and I pass bitmap info, I really want to do this. But other than that, it's exactly what I said it was, right? So now, when we get further through here, let's see what's going on here. Oops. Don't ask me why. I wrote that wrong. It's not what that's supposed to be doing. So now we just need to go ahead and clean up all of the mess we made. If we look in here about the V4, we don't want to do that. That was not what I was expecting to look at. Let's go look at the rest of it. There we go. So in dimensions require special texture. We need that to be exposed now. We want that to be like up here, basically. So people can call it. Ooh, is this done inside? Looks like maybe we don't want this here. Maybe this needs to be in here. There we go. All right. Okay. So now we're down to basically what I thought we should be, although, well, let me double check something. So this is the part that we haven't put that actual index vertex output thing in there, but let's just debug this for a second. Cover scale is wrong. We're now don't store that in the cover. We're just going to be doing it only at compute time. We've got these sprite values for up right here. We're passing the render group down. I don't know why. It looks like because of this stuff, right? So it needs to know what the X and Y axes are for the camera and stuff like that. And so we kind of need some way of getting that information passed down in here in a more convenient way. We will do that in a second. Finally, we need, in here, we need like the positions for the entities and stuff like that. So you can see that that's one thing I can't quite do. So this value right here kind of has to go away and it has to be reconstituted. That's actually fine. That's not a huge deal. If we go back to our push vertex, draw ground cover rather, where we're pushing our vertex on, that just means that that has to go in here. It's fine to do one add in there. That's not going to kill us. That's just moving it to wherever the entity is on this frame. So that's pretty easy, right? It's just a simple little transform to push it forward. So that's pretty simple. That gets that out of there. But we do have that one problem still. Whereas if we look at, again, this is just because we haven't implemented it yet. So those aren't errors. Those are fine. We do have this one problem still where we have to kind of think about what we want to have happen here. Why is... That's not cover P. Where is that value? It was called base P. Base P. There we go. So I think that's all good. And so this is really our only issue, where sprite values for upright with the render group there, that's an issue. It doesn't need it for anything too subtle. It needs it for the y-axis and the x-axis, right? And so it needs to know what's the actual up value for the camera, right? Like what's pointing upward as far as the camera is concerned. And then it needs the it needs to know what the world up axis is, right? And so the problem that we have here is, again, it's a little bit of like a partial evaluation issue. If we look at where the world up is being used, well, actually, let's look. If we look at where the world up is being used, we don't care about that because that's a constant. We don't change the world up, it's just what it is, right? So really the problem we have is with the y-axis h here. you can see that when we look at what's going on, that y-axis H, that has the camera up sort of lerped in there, because it's how we make our sprites be more forward facing. You know what I'm saying? Now, thankfully, the y-axis is usually the same. So what we could do is just pretend that that's not going to change. Now, it is going to change, because if we move the camera's like sort of focus level, it will change a little bit. But we could just say, well, it's not going to change enough, right, for us to care. So we'll just use it as it is. We could do that. The other thing we could do is recognize that, well, we could just reconstitute just this part at runtime. I'm going to say let's go whole hog. Let's pass these values down. And so in order to do that, I'm going to take this sprite values for upright. I'm going to create a separate version of it. And I'm going to say we're going to have this be a two-tiered call. So the first tier is going to be where you pass these things in, and there's no need for the render group. So the first tier is this. World up, camera up, x-axis H, right? And this tier, I guess I should have put these in the opposite order. And this tier is the one that actually does the work. So I get rid of these lookups into render group, and I just have you pass this down directly. Then the second tier is that you call this thing with just a render group, and it unpacks the render group into the call. That way people who don't want to do that, right, don't have to. They don't have to pass a render group if they don't want to. So then we end up with this. World up, camera up, x-axis H, and then these other pushes. World dim, align P, x-axis 2, y-axis 2, t-camera up. Right? So that's how that works. And now we can do these in two different waves. So now, instead of passing a render group here, we can actually just pass what we want to use for these other pieces of information, right? World up, camera up, x-axis H, world dim, align P, or whatever else. I'm sorry. Just these three. World up, camera up, x-axis H. And so we get rid of the render group here, and we say, well, what's the world up axis? Well, we know what the world up is, right? We've already specified that that's always this. What's the camera up axis? Well, hard to say, right? That's one that we probably want to specify a little more carefully. What's the x-axis? Well, that's really simple. We know we don't allow the camera to rotate, so in this case, we know that that's actually always the y-axis. So it's really just this value that's the one that we, maybe want to know. And if we want to know, like, okay, so what's camera up? What's pointing back? Or rather, what's pointing along the screen y-axis, if you will. We know that's just a subtly tilted version of the regular y-axis. But the question is, well, how tilted, right? And so when we go to update and render entities, when we look and see what those values actually are, oh, sorry, I didn't mean that. Update and render world. We know that we're doing our rotation using the pitch of the camera here to do a certain amount of rotation. So we know in the world mode that there's a certain amount of camera pitch, and that camera pitch is really the thing that determines what that tilt is. This value here is therefore sort of a magic value for us. It's a value that we want to actually expose to people who want to pre-cache sprites, because it's the level of tilt that we want to most of the time use, right? So that's really the value that we kind of needed to know. And so at the moment, we kind of, it's a little nasty because we're like, well, what's that value really going to look like, right? And I don't know where we really want to place that. But for now, we can be cheesy and just actually have this be something we specify. Default camera pitch, right, is this value here. Right? And then as a result, we can also do default camera up, right? And we can also specify what that value actually is. And so that backwards pitch there that we're actually getting, we can pre-compute whatever the rotation value actually is of our camera up vector. And then once those two things match, we can be a happy camper, right? So what I'd like to do is say, all right, this thing is something, right? We'll compute what it is, and we'll just say that we'll make these two things constants that we actually specify somewhere. Like that. Then in here, we say, happy birthday, everyone's, in a good mode. And then I think we're good to go. This has to take, all of the values I just said. And then I think we're clean. All right. So now, where's that default camera up? There it is. So now I think we're good, and I just need to implement the actual output layer, and that's pretty easy to do, and something that I have been wanting to do for a while. So inside the renderer here in the H file, I want to define that little vertex output thing, right? And what that's going to be is just a way of outputting quads and vertices. So it's literally just going to be like a, base index. Something like this. So basically something that says which index are we on for vertices, because we're going to have to sort of latch that forward, and you'll see what I mean by that. But then we just need this to understand, like, okay, when you output vertices, they go here. When you output indices, they go here. And then as we advance things forward, we update this value so we know how our indices should be adjusted to line up with the actual vertex buffer that we're submitting, right? And so we just need some way of making that work, and off we go. Now, I think that's probably it. Don't quote me on that. But if we now go ahead and specify these actual functions, if we now go ahead and specify these actual functions, you can see what we've got. We've got one that's called output quads, like so. Let me get that up from behind my head there. That takes the render group and the quad count. So we then have a vertex out, an index out, and an advance, like so, right? So now if I want to do this, I just have to say, okay, the vertex output, it just writes a vertex, so it doesn't have to return anything. It takes an indexed vertex output pointer that's like the sort of output param, basically. It has the vertex offset here, and then it has a p value, an n value, a UV value, a color value, and a texture value. It's going to write those out. And then we have a similar function for writing indices, like so. And it's really just taking the indices you wanted to grab for your quad. Right? Finally, we have an advance. And the advance just says how far forward did you want to go now that you've outputted some stuff, right? And that kind of wants to be that. This also wants to be that as well, probably. But we're going to leave it like this and assert, probably, is what we're going to do. Maybe this one as well. All right. So that's all the functions we need. And in theory, now we will get basically just like a compile that doesn't actually work, right? Of course, we haven't computed these yet, so we should. So we need to actually figure out what we're going to do here. That shouldn't be too hard. These UVs are just going to be like, well, okay, like that maybe is 0, 0, right, or something. This is like the min UV, right? So this is going to be like cover UVX. This is going to be like cover UVX, cover UVY. And that's going to be, 0 cover UVY or something like that, right? We don't really care. We'll just get that working. And then if these things are rotated around or flipped or whatever, we don't really care. But we've basically got what we want there. And now we need to actually implement the streaming. And so let's go ahead and do that. You can see we don't have any errors anymore except for the fact that we didn't actually write the functions that we said we were going to. Also, this should not be a pointer. I don't know why I made it a pointer. We want that to just return an actual little utility that you use. And so that should really look more like this, right? We don't need to allocate any memory or keep that around. That can just be something that's on the stack of the caller. And so that's really what we actually wanted. And so now the question is basically like, what do these things look like? I'm going to stub this out because this is going to be the more complicated one. These are the ones that are very simple, so let's do them. We know if we're going to try and output a vertex, you can see we've got our information here that's very straightforward. We know we just want to use, and if we go look at the index vertex output structure here, you can see what we've actually got. We know we're trying to write a vertex at something, so it's going to be this offset that we're getting passed in here, right? And then we want to write some part of this thing, right? And there's a bunch of these. That's what we're doing, right? So we want to write each of the things that goes in a textured vertex to make sure we've got them all. So we need a P, an N, a UV, a color, a texture index, an emission value, and a reserved value, right? That's everything. We're assuming that these aren't set at the moment because we don't know what they are or how they work. So we're not doing them. The rest of these are straight ahead. And so that's everything that we need to fill out for a textured vertex. So that's pretty much it, right? That's all we're doing. For index outs, now we have to output our indices. Those indices are into the global vertex array, so we want to make sure we know what they actually should be. And so in this case, we need to say, all right, the index offset, here we've got an index at, we're writing this one, and we're doing +0 equals I0, right? We're doing basically this. So we're just streaming out what those indices are supposed to be. But what you can see is these are not going to be, those indices are not going to be correct when we stream them out. They're wrong. Why? Because whoever wrote this, right, they don't know where in the global vertex buffer they are. They just know where they are relative to when they started outputting. So when they say 0, 1, 2, 3, what they actually mean is 0 plus some base value, right? And that's exactly where the thing that I added in there and said we'll talk about that later comes in. It's this right here, and so that needs to be added in, right? So what we really need is basically this. So all of those indices get, shifted up to the base value that the person thinks, like, in terms of, right? The person who's calling us is thinking in terms of some base value. They don't know what it is because they don't know where in the run of the program they're executing. They just know they're starting to output some vertices, and there could have been any number of vertices already in the stream. So that's just letting them not care. They can just give us indices that are relative to their starting position and have it work. So then when we advance, we want to do the same thing. We want to take our base index and we want to update that by the count that we're advancing. Similarly, we need to, and that's in terms of a quad, yeah, so that's in terms of quads. Now that I think about it, so we actually need probably to, yeah, we need to multiply that in two different ways. I should be more explicit. So this right here is a quad count. That's how many quads you're advancing by. So that means that the vertex at, right, is going to go up by the quad count times what? Well, how many vertices are there per quad? We know that there are 4 vertices per quad. However, we could make 2 versions of this too. One that does a more... so right now we're assuming you're outputting indices and quads and vertices together. If you were reusing them, we would have a second set of these that you give 2 different values. How many vertices you want, how many quads you want, right? And the same would be true up here. And so maybe in anticipation of wanting that, what we may want to do is actually sort of split this out. So there's one that you pass a quad count, there's one where you do vertex count, index count, right? Nope. And so here where we actually do that advance, we would say, okay, we want to make this be something where we call our sub-advance here with quad count times however many vertices we think there would be. That would be 4. How many indices we think there would be. That would actually be 6. Don't ask me why this is doing this. We need to change that in a second. Because that should be 6, right? Correct me if I'm wrong, but we don't have a way of outputting just quads. So I'm pretty sure when we do our push quad call. Yeah. Right. So actually, we need something like this. Oops. And so here where we take that base index, right? Same exact code. And that all looks good to me. I think that's really all we need, because this is just a known swizzle pattern that we use, and so I think we can just keep it like that. Right? All right. So I'm going to change to using that because I think that's a little bit better. I don't want to have to worry too much about that. So I think that's better. Then in here we can just say, well, we know it's 4 and 6 per, and so that's good. And then when we do our advance here, we will just say, all right, we know we have a certain number of vertices, so we're going to move forward by that many vertices. We know we have a certain number of indices, so we're going to go that number of indices. And then finally, we have a base index here, and so we know we want to update the base index by however many vertices we move forward, right? And so that's really all the information we would need to track. So it gets us down to basically just this function is the only function we actually care about. We do know we kind of want both ways, so we want this, right? And then in here, we would just say, oh yeah, much like we did this other thing, we're just going to say there's a version you call with quad counts if that's what you wanted. But you don't have to. So if you wanted to output something that isn't going to just be strictly based on unique quads all the time, if you wanted to do something like the cubes where there are shared vertices, you just can. And you would call the other version of it. So then we just need really this where we set the result of the thing that we're going to use for outputting. We need to be able to set that effectively somehow. And push quad is our key because that's the thing that is doing all this kind of work. So when we look at what's going to happen there, you can see how that works, how it's getting what it needs to get, and how it's doing what it needs to do. You can see here where the base vertex index comes from. It's that, right? You can see it doing this subtraction where it looks at how it's going to offset those. So we effectively have a vert index, which is, where is that? Here. Right, so we have a vertex index and an index index. You can see us kind of getting those things out here. And in fact, if you look at how we want to do this, we can probably just do this exactly as we were doing it here, effectively. We can basically just take this code and say, look, this is what we're actually doing here. Commands in this case needs to come out of here. Right? So then we're taking a look at this. We're getting this information out. We know we then need to advance these by however much we're saying we're going to eat up. And then we're saying we need to make sure that we didn't overflow, right? And that all seems fine as well. Finally, then here we're saying, all right, we've got our, I don't know what max quad texture count is really doing anymore. Is anyone using that? Yeah, so quad texture count is only something that people are using for special textures, right? And I'll be honest, I don't really care about that at all in here, right? So when we do output quads, we're just assuming that that's not occurring because quad textures are just not something we're managing, right? We're not using this for outputting like the cutscenes. That's not happening. All right. So when we come through here and we grab out the rest of this stuff, this is how we're finding out where we're actually starting, right? Like so. This puts us at the start of the things that we actually needed to check. And then we just need to take a look at these offsets here and make sure those are all okay. Now the other thing we need to do is the get quads call in this case. I think that's what it's called anyway. Where is that? There's like a thing we used to have for checking our pushing get current quads. So if you look at how get current quads works, you can see how it kind of does the work necessary to set us up for outputting things as necessary. And you can see in here we say how many quads we think we're going to need at maximum. And that just does a probe to check to make sure that we are going to have enough room to output what we said that we're going to output, right? So we want to actually do that. We want to, even though we don't really use it much because we actually end up using the vertex arrays directly, we don't really do much of this stuff at all. It's just the quad count we use. We need to make that call. Now, does push quad do that? I don't know. It does. So it uses the get current quads here and asserts that we have one. We don't really want to do that. We want to actually call get current quads because when we've come in here, we need to make sure that we're going to have enough quads covered, right? Okay, so when we come in here, we want to say, all right, let's get this from get current quads. Oops. We want to be able to call get current quads. We want to pass the render group, the index count, and the texture that we're actually using. In this case, we don't really want to supply because, again, that varies per batch. And so in here, we really would wish that we didn't have to do this. We probably need to start simplifying this code as well. It's too complicated now because it's doing way more than what we actually want it to do. And so when it does is special texture, I think what we want to do is just pass it a null texture here. But again, not great. So this code is not good, and we should fix it. And then here we know we have 6 per quad, so we can just do this. But again, we shouldn't be doing this anymore. We should simplify this to start thinking in terms of more efficient, less verbose things to do, right? All right. So let's keep going. For vert index minus vertex array offset, this entry here where we're getting our textured quads, I think this just needs to be safely truncated back to a uint 16, and otherwise I think it's fine. The output quads call here is supposed to be passing the render group, but for some reason I put the out in there. I'm not sure why. That was not supposed to happen, but it did happen. And finally, is base index to U16? It is. So actually that code didn't need to look like it was written at all, actually, so we can actually change that. This is all irrelevant. Okay, so finally I just need to pop back and change a few things here. In this case, we just need to do an assertion. Not sure the best way to do this, but I guess what we want to do is effectively this. Assert that if you were to add these two things together, or I guess like that, if that, assert that that is less than U16 max, right? So assert that that's not going to overflow our situation, then we're okay. There we go. And hopefully that'll do the right thing. The C compiler is always a little bit squinky. Finally, this is just, I think it's quad index out. And again, that's just going to do those swizzles for us. So I think that's it. We did a lot of code here. It'd be nice to test it, but we're pretty much out of time. So at this point, we're probably just going to have to do some very light debugging and then save it for next week, which is fine. We've done all the heavy lifting. But now we have to deal with the subtleties. And it also may inspire us to clean this code up a little bit now that we kind of know what's up there, and that's good too. I'm not sure what this is complaining about at the moment, but I think that's because I'd really, it's probably just asserting about something that we're doing. So I would like to quickly switch back to debug mode here, just so I can get a little bit of perspective on what's going wrong, and see if I want to tackle it now or wait till next time. So it looks like here we're getting some kind of a output problem with our vertex indices. Let me see what's going on here. So I think that So we should probably, this is sort of a separate issue, we should probably fix that. If we go to output quads and they give us a value of 0, we should probably give them back a value of 0 as well. So if the index count, or if the vertex count equals 0, and the index count equals 0, or I guess we should say, in this case, then we go ahead, right? Otherwise, we just give you back nothing, because we shouldn't ever probe there. All right, let's now take a look at the next error, or, well, whatever the error actually get. Okay, so in this case, in theory, unless I just screwed up that check, now we should actually be asking for some actual indices. Yeah, good. And so we gotta make sure this code works properly. I kind of just like hacked it together and it's probably wrong. But you can see here we get the command's vertex count. and we're updating it. I think the problem here is that this entry... It looks kind of bogus. Oops. It looks like really bogus. So if that's the vertex and index arrays offsets and they're at the base, then how the heck could we be that far in on the vertices in the command stream, right? Like, that just seems totally wrong. And so that just suggests that something's busted here, right? Like, it suggests that, like, I just, you know, the way I'm thinking of this thing is working is not correct, right? Because these things should be, in order for this to be true, these things would have to be quite different than they were, right? Because this is already greater than it should be able to be in that 65536 would have been the top value before these things would have had to advance. And so the fact that those things didn't advance doesn't really make any sense. And that's really the part that seems kind of strange. So given the index count was actually past something valid here, I'm just not sure what happened in there, right? If we take a look inside that, there we go. If we look inside here and see what's going on, you can see us sort of figuring out what's going on. It doesn't look like... So I'll be honest, I don't quite see how this was supposed to work. So this is just wrong. And I guess we just never hit this case? I'm not sure what's going on there, but this is actually pretty strange. So if you look at well, okay, I guess maybe I shouldn't say that. Maybe that check is good enough. I have to think about it. No, you know what? I don't think it is. So let's talk about that for a second, because I'm pretty sure that's just wrong. So if you look at what happens during get current quads, you can see where we're doing our check. Right here, we're saying, look, if we don't have a batch yet, start one, basically. Right, because that's happening here. So if we do have a batch, take a look to see whether you think we can fit these quads in the batch or not. But all we're looking to do is say, is the number of quads that we're pushing down this thing, do we think that's going to be, you know, higher than do we think it's going to be too high, right? And so if we look at how we're computing that, we're saying the max number of quads that could be in a batch is whatever the maximum 16-bit value is divided by 4. Because the assumption is that's when the indices would start to overflow, right? And I mean, I guess that's okay, but it assumes that we've never wasted any. Although I guess that maybe is true. So I don't know. I guess that is kind of true. You shouldn't, if you didn't waste any, you shouldn't be able to exceed this, but it's a little dicey. I'm going to run it one more time and see if I can see what's going on there. It's not really checking the thing we actually care about, but it may be sufficient, so it's hard to say. If we take a look at output quads here, sorry, on the crash, you can see that we're doing a safe truncate here. And when we look at what this value actually is, again, we're trying to compute the base vertex value. And so how many quads do we actually think we have sunk, right? The quad count is 7670. So the number of vertices, naively would be half that, right? So I guess the question is, well, if we then go and look at how many vertices we've sunk, it's way more than that. So the first question is, why? Right? So did we mess something up? So maybe we messed something up, and that's the answer. But let's take a look. So when we're doing vertex out, and when we do our offsets here, is there something weird that's happening where we're just recording way too many vertices? So you can see here where we call advance, we take however many quads we think we did, and we multiply by 6 or by 4. For indices and vertices, that looks about correct. The same thing happens here. We do output quads, we multiply by 4 and by 6 for our vertex count and our index count, and you can see that happening here. So that, again, seems pretty reasonable. When we say get current quads, what we really should be doing is passing these two values down. So I guess I say we want to streamline this code a little bit more, but you can see it's doing the exact same calculation we were doing here. So I really don't see that as being particularly an issue. So again, I'm not sure why we would be worried about this. So I'm not sure I'm seeing how we're pushing that many, how we're causing it to increase the number in such a way. This code isn't great, and we should just fix it, but I still want to just see if I can see what's wrong first before I clean it up. Like, I still don't see why we're not getting a vertex array offset that increases. It's like we're doing something that somehow bypasses the actual check. Oops. So in draw ground cover, right, we call this once. We say how many quads there are, which is correct. Once through each of these, we output the quad, and then we bail, right? And I really don't see why that would be causing a problem. Oh, yes I do. So that right there is an advance on a quad count. It should have been 1. So that's pretty much it. So that was just our bad. The implementation code was not at fault. We were. All right, so still getting the same bug though, so we haven't fixed the problem. That's a bit weird. How do we end up with, did that not actually rerun? How do we end up with the same bug with a different? Right, because that should have been totally different. Should have got a very different, we should have got very different numbers between those two. So that's a bit weird, to say the least. Right, because correct me if I'm wrong, but that's like exactly the same values. Which is ridiculous. That should not be possible. Between those two changes, we should have seen something change. And the fact that we didn't is very perplexing. So I think if we look at what's going on in here for our advance there, Although I guess, all right, I guess that's not true because the advance is only doing inside this. So I guess that makes sense. That was a bug, but it's not the bug, right? Because this is the only thing that's actually doing any advancing here. So I guess that makes sense. And then this code right here is the thing that actually is doing that advance. And so in theory, this should always match up with what this thing is thinking. But that's really the only thing that we would expect to have to check, right? So let's take a look at whether that's actually true each time through. So if we take a look at the entry, it's the first time through that we've done this, right? And if we take a look at the commands here, and we look at how many indices we've actually gone, you can see that the first time we get in here, we're at 3680, right? We're trying to add 256 vertices and 384 indices. So we're going to do that, right? And we've done that. And now this code actually should work, right? Because we're going to get a base index that's totally reasonable there, right? So that all seems fine. And it's only going to be the time, I guess, where we come through where we actually wrap it that this thing is not properly producing the change we would expect. So as we come through here, we actually are streaming out vertices, possibly even correctly, for quite some time. And then it's only when we actually get to the one that would overflow, right? That we actually trigger that case. And so it does look like this is a problem of us and getCurrentQuads are not agreeing, because getCurrentQuads here is the thing that needs to actually do this work. Now we should merge these two pieces of code is actually what should be going on here, but I want to debug it first and then merge them next week. So the question is, why is this not triggering? And, oh, do we just never update that? That's probably why. That's all. So since it's triggering off of the quad count, and we were just never updating the quad count. Now you can see how ugly this is because we're constantly talking about quads. We don't actually care about quads. We just care about indices and vertices. So we want to kind of simplify that down. So I keep saying we should just fix this, right? Oops. That's not where I wanted it to be. That's what I actually wanted. Right. And so, yeah. We just weren't updating the quad count, and the quad count's the thing that it actually cared about. But we kind of want to get away from that, and so I think we want to merge those code bases, those code paths, and just be talking about vertices and indices from now on. Because, hey, this thing could render triangles just fine, for the most part. And so we don't want to have it be, like, requiring that. Okay, so you can see that we're now running correctly, but we don't actually get the output that we expect. And so there's a little more to it than what we've got. I'll take a quick look at the debug, but then we'll go to questions because we can debug this next week. So the first thing I want to take a look at is what are we actually getting here for, maybe the problem is in the actual output, but maybe the problem is that we actually just computed complete crap values for our ground cover, and that they're not actually in places we would ever see. And so the first thing I want to check is just what are we sending down, right? Like, what does that look like? So I'm going to go ahead and take a look at the draw ground cover, and I'm just going to stop it right here. And I'm going to look at what it actually sees. So you can see that some of the times the texture handle isn't valid, so I'll stop on one where we know we're actually getting a texture handle, right? And then I'll stop kind of right here. So what can we learn from this? Like, is the texture index reasonable? It is. How are the UV values? UV values look totally fine. Well, I mean, they look okay, right? I can't vouch for them, but they look like the kinds of values we might see. Not sure what's going on with the watch window there. So that seems fine. Let's take a look at the general cover struct itself. We don't really care what the normal is, but it looks right. The bitmap we kind of know was okay. That's just white, which is a fine, non-modulated color, so can't really be wrong. And then if we look at these p-values here, you know, I don't think they're quite what I expect them to be. I'm okay. I mean, they're not like obviously wrong. They're not quite what I expected. I might want to take a quick look at what's going on with those p-values. So, oops, I wanted fill unpacked entity. I might just take a quick look. Why is this? Are these things like upside down or something? This should not. And in fact, that doesn't make any sense. That's not the way I wanted these to get output. So like this is wrong. It's not wrong in a way that would cause the bug that we saw. So that's definitely something to keep in mind. But I actually wanted it to be this. So we're gonna do it that way. Now it doesn't matter what those 4 points are, but that's what I was gonna do. So all right, I don't know for a fact that was not part of the problem, but it probably wasn't. So we'll double check, but I think that was just a minor winding change. Nope, that was apparently pretty important. All right, so if you look now, it looks like our ground cover is actually totally correct, other than the fact that the camera up vector is not right at the moment. So we do need to go set that, but then I think we'll be in good shape. If we take a look at what our clocks are now, what we can see is that, well, draw ground cover is still pretty expensive, but remember, this is in debug mode. So what I do want to do is do a quick O2 and just see if we've eliminated any of the problem. And then we can talk about the ground cover up vector. Okay. So now you can see draw ground cover it's quite a bit better than it was. It's still not perfect, right? It's still taking a little more time than I would like. But you can see that our total time is actually quite a bit better. It's, if we pause here, you can see that it's actually down where it used to be. And so even though this is taking more time than I would like it to take, it's way faster than it was. Before it was like quite a bit slower, right? So we've sort of succeeded. We got to change the orientation of those things, but we've sort of succeeded, partially. We probably could still do more than what we've done, but we're in good shape, right? We're in pretty good shape. All right, so we'll talk about the up vector. For now, what we can do is we'll cheese it. I'll just do this. We'll run the game, and we'll just copy in whatever the up vector actually was, right? That's not a good way to do it, but we'll do that for now. So here in Update Render Worlds, you can see us producing our render group, and then we're going to go down here and like do some stuff and set the camera transform, and then we're going to actually render the entities, right? So at some point, way down the line, we do stuff like, here, let's say. And we would know that the camera up is just going to be whatever it is in here, right? And so in the GameX form, I assume that was this value, right? I don't actually remember, but you know what? We can just look. So if we do get sprite, what is it called? Sprite values for upright. Yeah. So if you go look at sprite values upright, you can see the camera up is coming from GameX form Y. So really, we're just talking about GameX form Y. So it's this value, literally. And so we can just go ahead and copy those, right? So I can just copy that value and say that, it's that. and I can copy this value and say it's that. And now we actually have the correct camera up vector in there, right? And so now if we rebuild this, in theory, when we run, what we'll find is that we should have the correct facing values for our sprites, although there could have been another error in there, right? So we're at least, but that at least isn't the problem anymore. So presumably that's correct now. Looking at it, I think it's still a little wrong. You can see it looks a little sheared. Right? Do you see how it looks a little sheared across the top there? So I think what's going on there is our index output. It looks like one of our quads is backwards. And so that, we could also probably fix that, honestly. Let's take a look at how those indices are being output, but that's probably the only issue there. So I think we're almost there. I'm going to set the debug out here. I'm going to look at index out and just take a look at it. That is not the way I set it up, so it actually should be that. Let's take a look if that improves the situation. Still looks wrong with those indices. 0, 1, 2, 3, 4, 5. That looks right. That looks right, like what I would expect. I guess one of our P's could also be wrong, in which case that would explain the problem, but yeah, I'm not sure. It really looks like we're sheared there, like we're missing one of our things. I wonder if one of our p-values is wrong. I don't immediately see it. I don't immediately see it. Oh, yes I do. So again, just a typo. So yeah, not bad for a day's work. I think we pretty much got it. And we kept that on the fast path now. So now our ground cover pretty much looks the way it used to look. I don't see really any difference at the moment. And it's getting output in a nice streamlined fashion. So now like we're not hurting for ground cover. We're getting a real nice throughput there. And if we look at our frame timings, they're really nice. We're keeping, we're almost getting a we could actually do a 120 hertz at this level. So that's really good at this stage when we haven't pushed the optimization too hard. So I'm pretty happy about that, and hopefully that'll stay. One thing I'm not happy about is it looks like our computation for where the world gets paged in isn't great. It's too far afield, so we probably should adjust that view region, but that's not really completely irrelevant. So anyway, I think all that's looking pretty good. I'm pretty happy with that. Let's go ahead and go to the Q&A. Again, I would encourage you to try out the Discord instead of the Twitch chat. It's just usually easier. It's easier for everybody, and it's kind of more permanent, so you can use it offline easier. If you want to ask a question, head over to discord.gg/mollyrocket. If you have a Discord, you can just go ahead and join up. There's a Pound Live channel, and you could ask, ask your question there. All right, so X13 Pixels, actually, that's the fellow who wrote the debugger you saw me use on stream. He's asking if output quad should use an and rather than an or like what's the deal with that? And just to show you what he's talking about. Sorry, it's this code right here. And yeah, so The answer there is that since I don't know how this is about to be used, no, I wanted an or. The reason for that is, what if someone just wants to put some vertices in the vertex stream, and later they're going to put indices that refer to those, and they just know what they're doing, right? So while it's highly likely that an and is probably something that we could just do and it wouldn't matter, I don't really want to do that yet because I don't feel super confident that I know what we're going to be doing. So I just kept it with the least intrusive one. But yes, it totally would be fine, right? Valbus asks, so would the next step be to instance the rendering of the ground cover? So there's a couple different tacks you could take. It depends on what you want to do. But basically, yeah, if you wanted to make this even faster, because you started to run into problems with transferring, then, in other words, right now we've taken a step of optimizing just our handing this to the graphics card, right? So we try to really quickly write it into the vertex buffer. That's the dynamic vertex buffer that we render per frame. But obviously, there's more information that really needs to be there because frame to frame, we don't really change this stuff very much, right? All we're really doing is moving it based on where the entity moves. So if the entity moves, we offset it, but if that's just really 1-3 float value, so we really could just send just that 3 float value down. And so yeah, if you were really concerned about the transfer bandwidth of sending down all the vertices for those quads to the graphics card, the next thing you would do is try to cache that stuff on the graphics card. So you'd create a vertex buffer resident on the graphics card. When an entity came in and we did the unpack, we would write the things directly onto the graphics card and leave them there. And then when we go to render, we would just push on a thing that says, hey, go render that thing, and here's the offset. Now, there's a good reason why I don't do that right now. It's because that also does break up batches, right? Because at the moment, we would have to break up our batches to do that. And so if you really did want to move to that system, it's not as simple as I just made it sound. We would also have to start moving to a system where we have a fast indirect batch centralized loop, right? So that you're always pushing down like large chunks of 2 indices that are like how many things to render with what offset, and it's like an indirect rendering batch system so that we're not hitting the API front end too hard again, right? Because otherwise, every 64 quads, we're switching our batch for the ground cover, and we don't want that either, right? So this, as soon as you would switch to the instance rendering, you're also creating a new problem for yourself that you would have to solve, right? So you kind of have to be aware of that, right? And Pragma asks a related question, which is maybe it would be easier to do the upright sprite calculation in the vertex shader instead. Again, same thing. Yes, you can totally go that route, but you're going to take on a bunch of new work as well. It's not as simple as just doing it in the vertex shader, because if you're doing it in the vertex shader, that implies you've already got a fast way of doing the dispatch that allows you to switch those things per sprite, because that's changing per sprite. So, and whether or not it even happens is occurring per sprite. So again, totally possible, but not trivial. You have to actually, there's a bunch of work involved, which is why I'm not doing it, because until I know that we actually want that, we're inheriting a bunch of work if we do that we wouldn't otherwise need, right? Ryan asks, speaking of getting the compiler to output the right instructions, I've been toying with a lower level language assembly without the friction really. Would love to hear your thoughts. I really like the sound of that. I'm not sure I can give it much thoughts on spur of the moment, but I could certainly look at it offline. Here's pastebin.com ML2TLEAF. I would say it looks nice, actually. I like where this is going. Um, the only thing that came to mind when I was looking at it was I was going to say, don't be afraid of infix notation. Right? The reason that C infix notation sucks is not because it's infix notation. Infix notation is a lot easier to read than having to do like all of this, right? The reason C infix notation sucks is because it doesn't frickin' define what the assembly language is for it, right? So one way you could think about it is, and forget C, just forget, I mean, I'm talking about C, I'm just pointing it out as like a point of reference. This is kind of a little bit hard to read. When does it really need to be? Could you just have a nice infix notation that cleanly maps to a known set of things here that would be easier to read, so I don't have to read like add mul, okay, that's doing right, like, do you know what I'm saying? So I would encourage you to think about like, how do you make this easier to read what it's actually doing while still preserving an exact knowledge that it is 2 mobs a mul and an add in this order, right? Because I think you can do that. You just have to be rigorous with the way you specify how your operators work in infix notation. You could even have these be the infix notation, like mul, as opposed to times, right? So I'd say I like where this is going. Maybe like I would encourage you to think about, can you make it easier to read without taking away any of the specificity? Because that's where C really fell down. They made it a lot easier to read, and as a result, it's much easier to type in, but you lose a lot of the guarantee, because the compiler could do anything it wants. I don't want the compiler to do anything it wants. I want it to do what I want, and we lost that ability. So the question would be, can you add a layer of readability on top of this? Maybe even keep it so you can do exactly what you've got here. But is there a way to also be able to write an infix expression that's easier to read, but that someone who understands the language knows exactly what it comes out to be in assembly? That would be a really nice addition too, and somewhere that you could add, that's a good value add, right? That'd be my first thoughts on looking at it. That's all I've got off the cuff for you, but I like what you're doing. I think that's a great idea. I would love a better assembly language. Because yeah, register allocation, not really that important when we've got 16 registers flying around these days, right? In x86, x86-32, register allocation was a huge deal, and how you worked that out was a big deal. A lot of times now, you've got enough registers, it's not clear how much value there is to manually assigning them most of the time, right? So should there probably be a fallback in your language for I want to explicitly assign registers? Yes. Do we need them all the time? No. And assembly language unfortunately forces us to do it. So the problem you're attacking here I think is a good one. Let's get a little bit of the cruft out of assembly language, but let's keep the good parts. Great idea. I'm thumbs up. Any other questions? Do you ever feel like the veracity of passing around an often used pointer like game assets in HMH is too much hassle, or do you find it's more beneficial in the long run over a global? I'm glad you asked that question, and I think the real answer is that it is. The answer is yes and yes. The answer is yes. In general, C and C++ have a very hard time providing you the tools that you actually need to track how things are used, right? A global variable versus a function parameter are weak ways of saying something about the program, and they conflate two different things. One is whether or not I want to have to actually manually pass stuff around in typing it in. The other is whether I want the compiler to pass it for me, right? And so C++ added only one extremely weak version of this, which is that in classes, the this pointer is automatically passed for you. Why was that the only thing that can be implicitly passed? Why can't I just say that assets are implicitly frickin' passed, right? In my game, through functions that need them, up the call chain, right? And the answer is because the people who write these specs don't really know what they're doing, right? They don't think through what is a feature versus what is a specific use case somewhere. And so what they tend to implement as language features are actually specific use cases, not language features. And that's why you get this thing of like, should this be a global, should it not? A proper written language would never have to ask that question, right? You would never have really anything be global unless you didn't want to compute the address of it off a pointer. So it would be about performance, right? Not about whether it was a hassle to type or not. So really the answer to your question is that I tend to pass things around because I would like to know about the chains in which they are used. It's sort of like a functional programming style that's not really functional programming, but it's part of it, right? Should the language have made that easier? Yes. Did it? No, and here we are. I think you may have missed Pragma's question, or maybe I missed the answer. You missed the answer. Platin 21, how would you go about breakable surfaces, not like in a voxel style? That's pretty off topic and depends quite a bit on what you're talking about. Breakable surfaces, there's many things you could mean by that, and it really depends on what you're trying to do. There are many research papers on this topic. I would encourage you probably to read them. There was one pretty recently that was pretty cool, actually. I don't know if you saw it. It was called... Remember... Oh, man. I wish the web were good. Hold on a second. Thermomechanical. That's what I wanted. I never remember the names of these things anymore because my brain is too old. It's weird how you... Like, I used to remember everything, and now I remember very few things. It's unfortunate. That's just how your brain goes. Here you go.
In this paper, we present a material point method for visual simulations of baking bread, cookies, pancakes, and similar materials. Our model is capable of capturing characteristic dynamics of materials under baking or cooking process, such as melting, rising, cracking, and solidification. Here we show baking 3 loaves of bread with different slit patterns or with no slit. The dough expands and the slits open up during baking. And now we tear one of them open. In this example, we bake a tray of cookies with varying amounts of leavening agent and oven temperatures. Now we pour pancake batter into a pan, cook it, and then flip when the bottom of the pancake is solidified. In this example, we roast a marshmallow on the stovetop. The marshmallow is initialized as a homogeneous material, and we're able to resolve the distinct textures of its solid crust and melted center after roasting. We model the material as a solid, water, and gas mixture, and keep track of the heat transfer, water diffusion, as well as chemical reaction that take place during the baking process. The solid phase is modeled as a thermal viscoelastoplastic material. We use a modified temperature and porosity-dependent chem clay yield condition. A more porous solid mixture will have a smaller cohesion limit, and in the limit of zero porosity, we get a von Mises-type yield condition. Viscoplasticity replaces the hard constraint that the stress cannot be outside the yield surface to a penalty term instead. Instead of projecting the trial stresses back onto the yield surface, they are projected along the same directions, but only a portion of the distance. We demonstrate the effect of viscosity with a dough stretching and twisting example. Higher viscosity makes the mixture more sticky, which matches the rheological properties of dough. Here we demonstrate one of.
So anyway, you can go watch this in its entirety, but not suggesting you probably want to do most of that in real time because you probably have your work cut out for you. But point being, there's tons of these. The research community publishes many papers on breakable surfaces. And the bottom line is what you need and how complex that has to be depends a lot on what you're trying to simulate. If you just want things to fracture in any old random way, you can just split them with a plane in as many times as you want, right? Carve them up, and then use those chunks. It's a construct a solid geometry kind of operation, and you could do it, right? If you actually want some kind of simulation as to this is supposed to behave like an actual material, like with brittle fracture and cracks that spread and all that sort of stuff, then you are into finite element methods, and there's a lot of different ways you can do them, but you need to start learning some real physics, and you have to scale back the problem based on what you can actually do in real time, obviously, because for games it's different than in a research paper. But that's the basic idea. And like I said, there's a lot of them. That was a recent one that came out that was pretty cool. But basically, it depends what you want, Early in the series, said you want to try to make your own math functions. Have you gotten around to doing that yet? Only sine and cosine still remain. Those are the only two things we call. And we eventually will replace them, but I just haven't been motivated to go look at that because we just had much bigger things to worry about. Whereas those are kind of a known quantity. It's like you can always replace sine and cosine. You can even just cut and paste one off the web. There's so many of them. So I know that won't be much of an issue when we go to do it, but we will have to discuss it a bunch because we're going to have to do it from scratch, right? And so I just haven't been motivated to actually spend the time on that as opposed to other things. But those are the only two functions that we didn't implement ourselves. Everything else we did. So we're still calling the old sine and cosine, and we'll call the new sine and cosine once we implement them. Alrighty. I think that's about it. Let's wrap it up here. Thank you everyone for joining me for this episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along with the series at home, you can always pre-order the game on handmadehero.org, and it comes with the source code so that you can play around with it yourself and do your own experimentation. We also have a Discord now. I'll be putting some links to that up as we go, but if you do want to go to the Discord, that's just discord.gg/mollyrocket. It's got all of our stuff on there, and you can go ahead and log on to that and chat offline as well. It's a lot better than the Twitch chat because it kind of persists, and there's also different channels in there. So if you're trying to talk about something general, you can go to the general tab. If you're going to talk about something technical, you can go to the technical tab. If you're trying to ask questions live, you can go to the live tab. It just helps. it's a lot better than the Twitch chat for interacting with the folks. And also, I pop on there to moderate it from time to time to keep things civil, which I think is also a good thing, just to make sure that everything is pleasant. So I'd highly recommend you check that out. It's been working pretty well so far, and we'd like to get that to a point where it's nice and stable and everyone's happy with it. So do pop in there and give us our feedback as necessary. I noticed someone was mentioning that Discord is great, but we can't live without Instabot. I agree. It would be nice if Instabot became a Discord bot at some point, but, you know, beggars can't be choosers. So we'll see what happens. That's it for today. I'll be back here next week when we're going to take a look at putting lighting in. We've finished streamlining that process. So now we're going to put in some lighting evaluators into our pixel shaders. And we're going to see how much cost we incur from doing that. That'll start to give us some perspective on what we're going to have to do. Because now, unlike the previous pass on lighting that we did, this pass on lighting is literally going to light everything. It's going to light all the sprites as well as the rooms. So we're really going to be stressing that lighting path a lot more than we were. And we're going to have to see how that affects our performance, and we're going to have to take the corrective actions necessary to make sure that everything still runs smoothly. We want this game to run around 60 frames a second on a good machine. So we need to keep within the budget for that. That's about it. Until next time, thanks for joining us, and I will see everyone on the internet. Take it easy, everybody.